Michele del Zotto from Uppsala Universitet as our last speaker of the day, and he's going to speak about SymTFTs for continuous symmetries, nonlinear realizations, and spontaneous breaking.
Right. Thank you very much for having me here. It's a pleasure to have an opportunity to interact with you and spend some time in Cambridge. It's been a long time, so thank you for putting together this wonderful program. I followed many of the talks on YouTube. Very nice program, very inspiring, many interesting interconnections with very different subjects. And that's my main motivation to do a talk on the blackboard is precisely that I wasn't really able to gauge the audience. So I decided to do blackboard talk because it's more flexible. So if you have questions, feel free to interact with me, and I can kind of try to adapt to the audience while the talk is flowing. Over the past decade, we made lots of progress about the description of conserved quantum numbers of defects and impurities in QFTs. No? And so these progresses have been in very different contexts. So for example, one has a continuum QFT. This QFT can be Lorentzian or non-Lorentzian, and one can have a Euclidean, one can have a lattice, and depending on the context, the manifestation of symmetries is different. So for instance, on the lattice, say we have an Hamiltonian lattice, we have time, we have the lattice, and our impurity is just a special region in the lattice, maybe some special lattice point that propagates in time. And there, the symmetries, well, they are just maybe labeled by non-trivial configurations on the lattice, gammas here, that just commute with the Hamiltonian. No? In this case, these are some sort of flabby, topological, flabby membranes. Instead, in the context of Lorentzian, where we have time, where we have a space-time now, now the impurities are defects. In our field configuration, they can be defined by prescribing boundary conditions for our fields, and the symmetries of these are captured by topological membranes. They are and these are sigma. They are things that we commute with stress energy tensor. It doesn't cost energy to insert them in our correlator. We can move them. They don't have any displacement. They're just topological. But still,
it's very difficult to read the blue, so you should not use the blue.
I cannot use the blue. Oh, okay. Okay, thank you. So maybe let me just write the topological membranes. There will be some more general types. Fluffy. So the action here is by linking, or maybe by crossing also. They can transport the defect also by crossing it. The action of the topological membranes is very intricated, so the context of my talk for today's talk, I will be in continuum quantum field theory, and mostly I will have in mind Lorentzian examples, but it might include also Euclidean. Okay. So what I say is in this context, and it would be very interesting to understand how it generalizes in this more general context. There are some proposals in the literature, but I think it's very interesting to think about. It's an open question. So what is the point? The point is that these generalized quantum numbers Generalized quantum numbers have interesting structures, have higher structures. What does it mean that they have higher structures? These are like topological membranes, so they can end on each other topologically. They can fuse with each other and produce more membranes. No? And all these junctions and fusions of topological membranes occur in higher codimensions, are like topological membranes of higher codimensions. No? And so you start with a one topological membrane. It can start self-intersecting. And in that way it can create lower dimensional topological membranes that will also carry an action on the defects of your theory. No? So whenever you start and you find a topological membrane, that the topological membrane will come with some higher structure, and this higher structure can be non-trivial and can act on your defect. So there is actions on QFT spectrum. By spectrum I mean the collection of all possible operators, including the extended ones. No? So it is interesting for me, well, to determine the higher structure and also to determine how it acts on the fields. No? I really care about the action. I really care about what is the interplay of the higher structure with the spectrum of the operator. No? And this interplay is interesting because these higher structures that you can find, they are in a sense generalizations, if you like, of the 't Hooft anomalies. So the 't Hooft anomalies are examples of features of the symmetry that you can find studying the higher structure. But in general, you have more structure there, and the higher structure will have to match along RG flow. This is kind of interesting because you can use it to constrain RG flows. In a sense, you can, like, it's very natural. If you have something topological, you can make it big or small. It will be something that doesn't depend on the scale at which you prove the theory. So it is natural to expect that if you have a higher structure, which is or a generalized symmetries on topological membranes that are preserved along an RG flow, they will be RG invariant. So you can constrain the infrared if you know that there is some higher structure by matching the higher structure. Okay, so we want. So this is interesting. This is interesting constraints. No? Like the most important questions about quantum field theory are about what happens along an RG flow. So we want to compute this. We want to be able to.
Sorry, for the anomaly you mentioned, you mean the anomaly for defect or anomaly for box?
Sorry?
The anomaly, you mean the anomaly for defect or?
The anomaly for this symmetry.
For the symmetry.
Yes.
But the defect can bring new anomaly.
The defect can have anomalies supported on it. Yes.
Which one you refer to?
In that case, the defect would be something that is non-genuine, so it will carry some topological membrane attached to it, no? And so it will be in some sort of a twisted sector of my theory, and we can characterize those starting from these ones. So but in general, you can just have a symmetry that is anomalous on its own. You just cannot gauge it. Like an anomaly is like an obstruction to gauging a symmetry. So we want the ways to compute both the higher structure and to compute how it acts on the spectrum of the theory. No, this is like and so far there are tools to study this. There are essentially two approaches. One is a word-volume approach. And one is this topological symmetry theory. Okay. So word volume approach, well, there are many string theories in this audience. So this is a word that is probably familiar to you. Like it's literally how we study membranes in string theory. We can study this topological membrane starting from our field and just looking at what are possible topological actions that we can write down in various codimensions. And this gives rise to a way of describing these topological membranes exploiting some action formulas. And, or maybe you can just consider these TQFTs, you can stack them one on top of the other, and you can give rise to interesting higher structure by that idea. And then this topological symmetry theory is a different way, and this is related to what I want to discuss today. So let me just for my talk. No, this one. So how does the topological symmetry theory work? No, the main idea in the topological symmetry theory approach is that we want to exhibit an isomorphism between the theory that we care about, between the theory we care about, say, call it T, is our three-dimensional field theory, and we want to say that this theory is isomorphic to a bulk boundary system. A bulk boundary system. And the bulk boundary system is composed of various ingredients. There is two boundaries. And then here in the bulk, we have a D+1 dimensional TQFT. Oftentimes we denote it as D+1. Then here we have a T hat. This is a D-dimensional relative field theory. In the traditional, this is called sigma, it's called rho. Or this one is a D-dimensional. It's a topological boundary. Maybe in the talk I might denote it D sim. So what is the philosophy? The idea is that here we have our defects and we have our symmetries that act on them. And here, well, the defects are supported on this relative field theory. They are attached to some topological defect that extends in this bulk. They end somewhere here, and the symmetry is realized inside this topological boundary condition. So it is essentially a way of taking whatever is topological in the construction of these membranes and separating it from the way in which it acts on the theory by relegating it within a topological boundary condition. Okay? Yes?
Are you going to define a relative QFT for the...
Oh yes, like a relative field theory. A relative field theory is just a theory that exists on the boundary of a topological field theory. Okay. Like so. In fact, typically people would require that, like, to be properly or intrinsically relative, you would require that this TQFT has a higher dimensional Hilbert space on any manifold, and then or it has a higher dimensional Hilbert space. Typically, this is what characterizes the fact that this is relative. So it's not when you compute it on a manifold, it doesn't produce for you just a number, but typically a vector in the Hilbert space that this TQFT assigns to that manifold. No? So a TQFT is something that to a manifold of codimension 1 assigns a Hilbert space, and the fact that we say that this is a relative field theory just means that when we compute it on that same manifold, it is a vector inside the Hilbert space that this TQFT assigns to that manifold.
But once I pick...
once you choose this topological boundary condition, this is a way of kind of projecting that vector onto a number, if you like.
And then that's a QFT.
And that gives this isomorphism. No? But what I wanted to stress is that there are three ingredients here. No? There is this choice, the bulk, and the boundary. No? Three ingredients that you need to provide this isomorphism. No? So in particular, this theory is different from this one. Okay. So why is it useful, this approach? So this part here, the topological part of this picture, this part here, oftentimes is called a quiche. And this part here is called a sandwich, which is causing several problems, because it looks like out of two quiches you can form a sandwich, but there is a solution to this puzzle. This is not a quiche. Okay, so the quiche is only the topological part. This one is not a quiche, so there is
So you can form a sandwich out of a quiche plus
some extra stuff, no, which is non-topological. Okay. Now why it is useful in mathematics? This is useful because the formalism of extended TQFT is well developed, and this part here, the quiche part, which is the part that can have a saying about the higher structure of the symmetry, this part here is fully mathematically well defined, like, according to the mathematician you talk to. As always with mathematics, it's the function of the mathematician. So this part is kind of well defined. So it gives rise to a way of having some mathematical structure in this gadget. You can import all the mathematical language that has been developed to speak about extended TQFTs in this context. And physically, it is useful because oftentimes it is possible, for instance, to classify gapped boundary conditions for TQFTs. And if your infrared is gapped, then this side will also be a gapped boundary. And then you can study, for instance, phases that are compatible with certain symmetry structure by just studying these sandwiches where you put two topological boundaries on the sides. No? So this is something that can be done very effectively and give rise to some sort of generalization of Landau paradigms and stuff like that. Yes?
Can you also do for the second case when the topological operator intersects with the defect?
This one?
Yes.
Yes, absolutely. Yes.
What is the picture?
Oh, you would just have the same. It's literally the same. So in this case, you would just cross. So the whole structure of the topological defect that will act on your fields are supported inside of this boundary. You know? So don't be fooled by my drawing. Yeah? This drawing, this one is a d-dimensional. It looks like a plane, but it's a d-dimensional space. So here within this space live all the defects, topological defects that can live in d dimensions. Okay. So you have a crossing action also there.
And I'm sorry, so if the red line is not the topological defect,
yes,
that intersection looks not topological.
Wait,
But
this part, this one is not
Yes.
topological, this one is not
Yes.
topological, but the ending here, this one is ending on some topological configuration
Yes.
in this part.
Yes.
So this one is topological,
Yes.
this one is not.
Yeah, but the thing I'm worried about is whether the intersection is topological or not.
Here, the topological data about the action of the symmetry on your defect is captured. Here comes the information about the actual position of your defect in space-time. This part cares only about whether it links or not, or whether it crosses or not.
That's essentially my worry, but initially that point may not be topological, the intersection point.
This intersection point.
Yeah, but in your right-hand side figure, it seems it's always topological.
No, in my picture, also in this picture here, this yellow membrane is topological, so the intersection point is topological. The intersection point of that along the defect is topological, so I can move it around and it doesn't change my correlation.
So you assume the red line preserves the symmetry?
I'm assuming that the red line preserves the symmetry. Yes. Thank you. Yes. Thank you.
Okay.
There might be variations of these pictures that are more interesting, but I won't have time to discuss them now. It would be interesting to discuss it later. So how are these obtained? Typically, they are obtained by starting from a theory with an anomaly. You have a finite symmetry. You start from a theory that has an anomaly. You couple it to it by turning on some background with anomaly inflow, and B is like a background for finite symmetry, and you can gauge it. So you can gauge it here. And here you impose, so this becomes this sigma of some dynamical gauge field. Here you impose the boundary condition, and you attach the anomalous boundary here, and then you just switch off the background. You just switch off the background, and so in a sense, like these SymTFTs are often obtained just by gauging, promoting to dynamical some bulk finite gauge fields. The operation of gauging a finite symmetry is topological. So you have a machine. Whenever you have a theory that has an anomaly, you have a machine to produce symmetry TFTs for that. However, like this doesn't work. This framework is very well developed for finite symmetries, and as is the theory of extended TQFTs for one can use to study this problem. However, in the context of the theories that I'm interested in, Lorentzian continuum QFTs, oftentimes we have symmetries that come in continuous families, continuous global symmetries. No? They are like the first example that people that study high energy encounters when one studies symmetries. They are associated with nether currents. They are a very well developed theory. However, they would never fit in this paradigm as I described it right now, because gauging a continuous symmetry is not a topological operation. There is no topological fit theory here that I can do if I just promote it to gauge. No? Whenever gauge a continuous symmetry, we produce new degrees of freedom in the spectrum. There are solitons. It's a complicated operation. It's not topological. So, and we know that there are many examples of theories that have this, and there are also examples of theories that have interesting infinite families of symmetries that wouldn't fit in this context, like the chiral symmetry of QED or the Hopfian symmetry of the CP1 model. The examples of symmetries that wouldn't fit in this paradigm, and so this puzzle was addressed and discussed in this paper by Antinucci, Benini, Brennan, and Su. The first time that this was discussed. And our contribution was to extend this to the case of non-abelian continuous global symmetries. This is what I want to discuss a little bit today. And so what was our approach to address this question? Our approach to address this question is essentially to consider a controlled scenario where we can derive what is the quiche. No? So from what I told you, like this quiche part is essentially just a feature of the Higher symmetry. No? It doesn't depend on the relative field theory that I put here. No? So if I want to characterize what is the quiche, I don't really care from what theory I start from. I don't care whether this theory is special some kind or not. No? And so our approach was to take some example that had supersymmetry and use the fact that these have holographic dictionaries to read off what is the candidate for a SymTFT. So if you don't know what is holography, so our strategy is essentially that the quiche is independent on the choice of T hat, and so we can use holography. So holography is like a dictionary between conformal field theories and gravitational theories that was born in string theory. I won't like there are many experts in the audience about it and that know holography much better than I do, so I refer to them if you have questions about it. But the main philosophy is essentially that you have some sort of a dictionary between gravitational theory in ADS and a CFT in the dimensions. It's another of these isomorphisms. And yes.
So here, in general, is there some baby example? Like if I just have a global theory with a global symmetry, like
yes.
honest zero-form symmetry, how does the symmetry? Is there some special? Is it some special case of the SymTFT?
Yes. Yes.
And is there any, for instance, if I self-intersect a global charge, can I know that I never get higher codimension topological defects that act non-trivially, or that I can sometimes?
In fact, sometimes you can. Like in the, especially if you have a Tufte anomaly, what we show in this work is that you can have self-intersections of the topological defect that can capture that.
Okay, could you give an example? I don't know if it's too much out of the.
I will give examples later on, but thank you for the question. Like there are plenty. So well, let's see, like holography. Yes. So in this context, there is a dictionary that says that whatever dynamics is inside the bulk is gravitational theory. It corresponds to the dynamics in the CFT, and it comes because the boundary conditions of ADS are governed by some conformal symmetry. So you can map. And define a map between the two sides. Like slightly more precisely, this map has been refined recently in these references. The idea is that if you think about what string theory does, really, it constructs a relative field theory. So it constructs some sort of a map that depends on choice of boundary conditions, and these choices define a relative theory more precisely. And yes.
Yes, I missed the basic point. The Kish has an energy momentum tensor?
No, it does not.
So how does this work? So the Kish is the boundary of ADS?
No. Like no. The dictionary between ADS and the theory is literally ADS is essentially here. It is equal to this picture.
Yes.
Now, if you think about the way in which these correspondences arise in field theory, in string theory, you see that oftentimes if there is torsion on the internal geometry, the fluxes of the various fields involved, they don't commute, and so you have dictionaries of this kind that depends on choices of boundary conditions that are not commuting, and so what you really end up engineering is this side of the picture. So you have a dynamical theory coupled to some bulk, and that has a vector space of boundary conditions. And then the idea is that, like, since all the fields in ADS will asymptote to trivial fields on the ADS boundary, you can somehow isolate some region here where only some topological long-range fields survive and are responsible to explain what is the dictionary between the choices of boundary conditions for your gravitational theory and the choices that makes this relative field theory into a field theory. No? So it's very subtle. It's not obvious. I don't think, like, oftentimes you find the statement that the SymTFT lives on the boundary. It's kind of fuzzy there, I would say. Like, but there is a way of taking, like, limits of fields in ADS and extract some topological long-range part of them, and those are responsible for matching the possible choices of global forms here, there, with choices of boundary condition in a topological field theory. And so it is in this sense that there is a dictionary. And so in particular, like this dictionary kind of instructs us to go close to the boundary to see whatever survives. No? And if you have a theory that has a global symmetry, continuous global symmetry here, maps to continuous gauge symmetry there. No? And so, like, the question is, what happens if we take this continuous gauge symmetry in ADS? So this Young Mills in D+1 dimensions, but it is in ADS. And so we have our Young Mills action, so this. And what happens to this when we go close to the boundary? Is there a way to extract some limit? No? It has a coupling, no? Like this. No? And now, with this in mind, it is useful to think about the metric of ADS as something that goes like in some coordinates, which makes it conformally equivalent to the flat metric. This is Z, and then we have ds d minus 1, 1. This is flat. This is a metric that we call ds tilde. And with respect to this choice of coordinates, this action here becomes essentially minus 1 over 2g squared. And then you pick up factors ld minus 3, zt minus 3. And then you have trace of f wedge star f, where now the star is with respect to this flat metric. Okay? Yes?
So, I mean, if the goal is to study continuous internal symmetry, like, I mean, are you forced into a situation where you consider graphing the bulk, or can you just have like some, I don't know, some continuous analog of this?
Yes, like I think so. Yes, like there is. In fact, this is the approach followed by Antinucci, Benini, and Brennan and Su. No, so you just say let's cook up a TQFT that does this. No, and like in a sense, it's viable. No, you can subject this to tests. No, and but in our case, I kind of wanted to stress that this kind of comes from above. No, it's not like it's not like you can postulate that something like that exists, but when you postulate it, there are a lot of subtleties in this non-abelian. These are the theory that we end up with are some non-abelian BF theories or abelian BF theories of Horowitz type, where some non-compact and compact gauge fields enter, and they are like questionable somehow. Like they are not TQFTs. They don't have finite dimensional Hilbert spaces oftentimes. What is that, and why do you want to consider that? Well, because it has the operators that it should. No, that's a good answer, I think. Another one is also that somehow, like, you can argue that it's a good proposal, no? And we can use holography, for instance, to do that. No? And then, like, so if you want to extract this so you want to go. This is the ADS radius, this L that I wrote down. And we want to go close to the boundary. So we want to take this z to 0. And you see, like, yes?
Is there any reason you choose to put Yang-Mills rather than Chern-Simons in the ideas?
It's a good question. In the context of holographic dictionaries, like when D is high enough, you expect that the dual of a continuous global symmetry is just a continuous gauge symmetry. Gauge symmetry without any Chern-Simons coupling. It's just the most vanilla case. No? Sometimes, if D allows it, you can turn on Chern-Simons couplings, and that's interesting, and that is related to when you have anomalies for the generalized symmetry. There is an example that I want to discuss in what follows, which is related also to his question, where if you include a Chern-Simons coupling or generalize the Chern-Simons coupling, you end up with some defect that would have some linking that is sensitive to the anomaly. Okay, so if you are in a vanilla case where there is no anomaly, when you start without anomaly, I wouldn't expect to have a Chern-Simons coupling here for G. So now we want to take this limit where z goes to 0, and doing that is not like in these variables is a bit complicated. No? If z goes to 0, this expression makes no sense. And so there is a nice Hubbard-Stratonovich transformation that you can perform. Where we introduce some extra field, and then where now B is an auxiliary field. It's like a D-1 form valued in the Lie algebra. The Lie algebra of the continuous symmetry. And you see that in the limit when t goes to 0, this part here dies. And you are left with this type of action. This is an explicit example of an action of this kind. And it's a well-known action. It's called the Horowitz non-abelian PF theory. And this is essentially the most natural proposal to plug in as a D+1 dimensional TQFT in this bulk. Then one can run the type of consistency check that Buiker Martin was asking about. So this is a good choice. And is a good choice. One can start from an action like the one above. So we start from supposing that our action is like raise of b equals f. But now we remark that in the limit in which we restrict ourselves to this theory, we're essentially projecting on flat connections. So we are projecting on flat connections. In the limit, we are projecting on flat connections. Which in this case is enforced by the B equation of motion. They will make them vanish. And then the B field will so A has the usual gauge invariance, is our gauge field started from, becomes. Now also B acquires some gauge invariance. B transforms like this. Where this d tau is auxiliary gauge symmetry that you have on. It's a D-2 valued the algebra of it. And of course, the transform into the adjoint, so this symbol here is literal, which is just the usual covariant derivative. So if you look at this theory, similar theories have been proposed for the U1 case. And in that case, the B is just a real Higher form, and this one is a usual U1 gauge form. One could look at the topological operators that one has here. And this theory has, well, the Wilson lines, of course, closed loops. They are topological. And the reason is some sort of generalized version of non-abelian version of the Stokes theorem that holds in this case. Just move them, you pick a contribution disproportional to the connection, but the connection is flat, so it doesn't depend on the shape of the path, just on the endpoints. And then there are some codimension 2 operators that we call B operators in the vectors. These B operators are operators that support a TFT on their own volumes, which is essentially something like this. You have a path integral on some new fields that are supported only on the support of these defects. And they have some interesting actions of this type. So where U, x0, U inverse. So U and beta are extra fields that are supported on the support of the defects, like a TQFT on its own. And B and A, they are pullbacks from the bulk gauge fields on the support of the defect. One can check that these are topological. And the U is just a G-valued form, and beta is a G-value, is Lie-algebra value. So this one has supported, it is D-1. So this one is D-1, and this one is D-2. This action is written in D+1 dimensions. Okay. So one could ask, what are these? What are these? And in the it's really easy to show that, well, not that easy. One can show. We do it in the paper. That these operators will have the right linking that one would expect to kind of recover this type of picture. However, by gauging variance, one end up, one can show that these operators, these ones so here, this is a closed loop, this is a closed surface, there is no boundary. Here one can show that the correlators here of Q of X naught sigma and W are gamma. This one essentially goes like the character in the representation R of e to the 2 pi X naught normalized by the character of the dimension of the representation. So it's not exactly the action of a symmetry that we are after. Like we were expecting that this codimension 2 operator would correspond to the action of the standard zero-form symmetry on our operators. Why is that? Well, the answer is in this picture. So in the bulk here we have a version of this BF theory. So we have some flat gauge theory in a sense. And so these operators, like the operator here, for this reason, they don't depend on the choice of an element in the Lie. X0 is an element in the Lie, no? It's an element in G. No? And they end up depending only on its coadjoint orbit, so because of gauge invariance. No? And that's related to the fact that this is a flat gauge theory, so in the bulk you must have gauge invariant operators. Okay. So in order to have something that can implement a symmetry transformation here, you need to remember about this picture. We said that indeed the symmetry defects are living within the boundary. So what we want is not something gauge invariant, because on the boundary the gauge transformation will trivialize. So the boundary here we can have some Q of X open, say, that are just confined, stuck on the boundary, and when we try to pull them out in the bulk, they come out attached to a surface. The surface is topological, so but they are not genuine operators in this bulk gauge theory. They come with a topological surface that attaches them to the boundary. When you put them back on the boundary, you get an operator here which now does not depend anymore on the conjugacy class. It literally depends on the choice of the group. And with these ones, if we have a Wilson line, I wanted to have it color coded. If we have a Wilson line that stretches from one side to the other, a given representation, we can show that the analog of that formula becomes literally the symmetric transformation of the Wilson line. So we have this is an open Wilson line. Open Wilson lines are matrix valued. No, they are not. If you have a closed loop, it's a scalar. But now these are open, so they are matrix valued. And here in the physical or this relative field theory, the endpoint will be our operator, which is transformed in a representation R of the symmetry. Here, it's Dirichlet boundary condition, doesn't really matter. When we cross, it becomes trivial. When we cross them with this operator, we pick up a linking, which maps this operator into a representation, linear representation of this type. And to undo this one transforms. So in this way, we implement linearly realized symmetries. By just a sandwich picture.
Sorry, where does this surface end? The surface which on one hand is attached to Q.
This is not there.
Yeah, that one.
This one ends along a defect of codimension 2 inside of this topological boundary.
On the other side?
On the other side, it doesn't. It's just topological. So it doesn't attach here. It just if you try to, what I was saying is that if you try to pull it out, it doesn't doesn't come out of the boundary. If you try to pull it out, it comes with a surface that attaches it back to the boundary. So this motion is not allowed. It doesn't produce a genuine operator, but it's a genuine operator on the boundary. And its action on the symmetry precisely implements the linearly realized symmetries. In the case, if you have so this is good. In the case you have an anomaly, you can introduce a Chern-Simons coupling like before. So you take a PF theory. Say that you have a theory that has a 4D theory with a U1 times SU2 global symmetry, but with now an anomaly of this kind. Then you can reproduce it by just adding some fields, DNF, the analogs for the abelian case, and then you have our trace of DNF for the SU2, and then you will have a term which is a Chern-Simons term like before, of this kind. And so building on work by Caidi, Nardoni, Zafrir, and Zeng, we expect that Caidi we expect that anomalies can be rid of from higher linkings in the bulk. And one can indeed see that in presence of this coupling, we can study inserting these Q of x zeros for the SU2 and some Q of some x small 0 for U1 on a surface sigma tilde, and find that this one is proportional to some exponential factor. Then you have a linking between the self-intersection of sigma and sigma tilde. So we are in 5 dimensions, sigma is 3-dimensional, it intersects itself along a curve and another 3-dimensional membrane have a linking number in 5 dimensions. And then there is a factor which is proportional to k, I, and some function of the backgrounds. So when there is no anomaly, this higher linking number cancels. If there is an anomaly, you can detect it. All these computations are done explicitly in the paper. This okay. However, we know that continuous global symmetries are not always just linearly realized. You can also have non-linearly realized symmetries. And we learned it from masters. There is this beautiful couple of papers by Callan, Coleman, Bessel, Zumino. So one could ask, what about non-linearly realized? How do we fit a non-linearly realized symmetry in this framework? This was the result we thought about it. It's very closely related to this second paper by Altinucci, Benini, and Ricci. So they had a proposal where you start from these continuous global symmetries and you obtain this sort of universal chiral Lagrangian, if you like, for your symmetry, for your generalized symmetries by studying some sort of holographic version of the SymTFT. But we wanted to do it in the sandwich picture. The result is very closely related. If you want a non-linearly realized, so this comes with a Callan, Coleman, Bessel, Zumino topological boundary. So here, when I had the symmetry that was linearly realized, I just put on the symmetry boundary, I just put Dirichlet boundary condition, a trivial boundary condition, if you want a symmetry that is non-linearly realized, the idea is that you put on this symmetry boundary some degrees of freedom of some topological degrees of freedom of its own. So we have to add an action of this type. B minus A. This one caps with the B plus B and beta. Again, we have some fields that are supported on the boundary. So V is and then there is an extra term, V which stays. So this includes everything, and then there is B which A. So V is a G-valued zero form, and beta is a Lie algebra valued D minus 2 form. And this one has a symmetry transformation like this. This one also has gauge redundancy. Very similar to the volume theory that we found in defect, but just now we use it to define a boundary condition. No? And in this case, if you choose to support this topological degrees of freedom on the boundary, then the Wilson line has an ending also on this side. So on this one, the Wilson line representation R will end on a function of the topological fields. Okay. Then, if you want if you have a theory where the symmetry is non-linearly realized, the way in which this universal part of the sigma model couples to the theory depends on how you choose the physical boundary conditions here. And there is always a choice that reproduces the universal action by Callan-Coleman Ressentimento. So that one is in the paper. You can look at it. So we can recover that aspect. And then the other thing that we wanted to include in the formalism is another feature of continuous global symmetry is the fact that they can be spontaneously broken. And when they are spontaneously broken, you have families of vacua. And that's also problematic in this context of the SymTFT, because when people study the SymTFT, typically they study it on field theories that are supported on space-times that are compact. So in this picture, I have an interval. This interval is times space-time, like MD. I have an interval like 0, 1 times a d-dimensional space-time. And this space-time is compact, so there is no boundary in particular. So when people study SymTFT, this is the setup that they have in mind. No? Now, if you want to break spontaneously a symmetry, then you need to do it dynamically by choosing boundary conditions. So if you want spontaneous symmetry breaking, you need a non-zero boundary. No? And so the structure of the sandwich changes, because we land on a scenario that has boundaries and corners. So we have this would be the boundary of M. No? We have our this is our hat, if you like. This is our B-sim. But now, so you see, like we have also another. So this is like, if you like, B-sim is supported on 0 times M. The hat is supported on 1 times M. And now we have another boundary, which is I times dm. Okay, this is the interval. We have this M has a boundary. Now we have a boundary for dimension 1 here. We call bilateral. On the side is lateral. It's also topological, because this is the bulk remainder is always topological. This is topological. And then, so this is codimension 1. Then we have also boundaries in codimension 2. We have some corners. here there is a corner, and here there is a corner. This is like 0 times dm, and 1 times dm. This is a physical corner. This is a topological corner. Okay. So you see, like the physical corner is responsible to tell me how my choice of boundary conditions couples to the bulk. It's like a black box for me. But on the left-hand side, we have the symmetry boundary, the one that decides what type of representation I have. But then I have also this B-lat. That one is another topological boundary condition. Like all the D+1 dimensional bulk system has to be topological. So that one is another topological boundary condition. And then I have a corner here. So this one is since everything is topological, I should think of this as a topological interface between the symmetry boundary and this lateral boundary. So the claim would be that the spontaneous symmetry breaking is realized by this interplay. Does it work? Do we have do we get a sensible result? This is something that one can study explicitly because we know some boundary conditions in this context, and we know what we want to happen. So we know that if we act, so we know that if we have some charged operator here, this will have an O here. This O will be our order parameter, no? And so we know that if the symmetry is unbroken, we want to be able to create a symmetry defect here. We create it, we evolve it topologically, we move it here at the price of linking it topological with the endpoint of the Wilson line. We move it to the boundary, and so we start from something that is like a correlator of O. When we cross O, we pick a phase associated to its charge, something like this, O. And now, well, if my defect can be absorbed at this corner, then I'm not changing boundary conditions here, and I end up with a word identity that sets O to 0. But if instead, when I move my topological defect on this corner interface, I change it, then here I'm changing the label of the boundary conditions, and I cannot conclude that the order parameter VEV is 0 anymore. Okay, and so we have a guide to understand which boundary conditions and which corner TQFTs corresponds to having the symmetry broken or unbroken. So for example, if you have a U1 uniform symmetry, we have a broken. So this is a B sim, this is B lat, this is our corner sim. And so this is setting the symmetry, so we choose some sort of generalized Dirichlet boundary conditions for the A fields, for the gauge fields A. And then here we have some generalized Dirichlet boundary conditions for the B fields, where this symmetry defect will trivialize. So this one is a case where if I take this is a Q operator, when I push it on the boundary, it trivializes. So in this case, the interface is dA dB, and this one we can show it can absorb the symmetry generator. We can show it explicitly. You insert it in the path integral, you use the Wolf-Bohm approach, and you show that the corner theory that we obtain is capable by a gauge transformation of eating up the defect. Yes.
So for the moment, as long as you have a physical boundary there, the symmetry, you don't know if the symmetry is spontaneously broken or not, right? Typically, what we do.
Yeah, this is what detects it. Is the other boundary.
Right, but what's the procedure I should have in mind? Should I have in mind that the physical boundary then is brought to infinity and you're left with the interface that still detects if the symmetry was broken? Because if I think of the procedure, right, I typically put like whatever, magnetized boundary conditions.
Yes.
And then I only know if having the broken symmetry once I push them.
Once you push them at infinity.
So I forget about them and I see if there's an expectation value. So this process of pushing them to infinity, what is it here?
Well, it's related to this endpoint, which I don't have time to discuss. But the details are in the paper, so we can discuss it later if you like. It can be done. Also for the Wilson lines, so you can start with a Wilson loop, make it infinitely big, and see that this happens. So it's related. Another subtlety in this picture is that everything here is in the Euclidean. So spontaneous symmetry breaking happens only by choices of boundary conditions at infinity. But in this case, which should correspond to the broken case, we find that we have corners that are corners between the A and the A, but these ones are labeled by a parameter, and this parameter is shifted by this action. Moreover, with some further work, in the case of p equal to 0, you can see that this parameter really lives in R mod 2 pi t, which is what you would expect for the Goldstone boson of a zero form U1. And for p greater than 0, you can see that you have something like p forms modulo closed p forms with periods that are integer modulo 2 pi, which is more or less it's more or less the target of a sigma model that you would expect for a higher dimensional p form gauge field, morally at least. And in the case of non-abelian G, we can also see that the unbroken interface is unique, and if you break G completely, you have an interface like this, and this psi then is literally a parameter in G, so corresponding to the full breaking, and you have indeed boundary conditions that are labeled by this. It's consistent. The case of partial breaking we haven't done. But it's an open direction we are currently considering. And so, open direction that we are currently considering, well, extending this scenario to include the generalized symmetries that are non-invertible, how do we spontaneously break them and study that interplay. Include also finite symmetries, because this setup of a SymTFT with boundaries and corners hasn't been considered that much so far. We would like to consider some consequences of these generalized word identities. So I told you that we have some, like, if this corner is acted upon, we have still an expression. It doesn't kill the operator, but still like is a relation between correlators with defect operator insertions, and it might be interesting to understand it a bit more. And then, well, the interplay with the RG flow. No, what about what happens if you start flowing this theory and study their basis? So in summary, like it's like the structure of the quantum numbers of extended defect and impurities are kind of encoded in various ways in topological memories in the context of relativistic field theories, and exploiting field theory techniques that we are very familiar with. We can study them, and we can capture their hierarchy structure. We can study how these quantum numbers behave. And in particular, we can study how they act on the operators of our theory. That's probably the most important part. Like oftentimes in the mathematical treatment of symmetry categories, the action of the category on the space of fields is somehow forgotten. And instead, like for us, it's very important, especially if we are interested in really constraining the behavior of defects and impurities. So with that, I think I can conclude.
Thanks, Michele. Maybe we have time for a few questions. Maybe I'll start with one. So basically, there is this accident that pure gauge theories for finite groups are topological.
Yes.
And then you say, okay, I want to build a sandwich, but I'm used to liking topological sandwiches. Therefore, I want to do something like this, but of course, Mills has a kinetic term. one thing you can do is you restrict to flat connections.
Yes.
And that's fine. But are you sure that you're not missing anything by just restricting to flat connections that is intrinsically meaningful to the symmetry, like coupling to background to bundles that have non-trivial degree or something like this?
Absolutely.
Because I mean, in the supersymmetric setting, people have been looking at these setups since the early 2000 maybe, and there you have this feature that you want to twist, and you say, okay, this setup with pure gauge theory are too complicated, but I can twist, I only isolate, and I'm going to throw away most of the theory, but I can at least play with some flat connections. And then you can play many games, but you certainly don't claim that you're capturing everything about the symmetry at the boundary.
Yes.
So the question is, and that's all, you present an holographic picture. Is this like, is it an argument to say that most of what you want to capture about the symmetry is captured? Or is it just a belief? Or is it just, what's your take?
Thank you for the question. It's a deep question, as always. So, what do you want from the SymTFT? No?
Yeah.
In the topological context, for instance, there are boundary conditions that capture the gauging of the symmetry. This Neumann boundary condition.
Yes.
If you use a Neumann boundary condition here, the result will not be the corresponding theory with the symmetry gauged.
Yes.
It will be some sort of average over flat connections.
Yeah, that's right.
No, but you will lose a lot of information there.
Yeah.
So, however, if you have an anomaly, there is an obstruction also to that process, which is captured by this triple linking, for instance.
Yeah, I get that, yeah.
So some features
Yes.
can be characterized topologically.
Yeah.
Other features that are more dynamical, I don't think so.
Yes.
As far as coupling to backgrounds, as long as they are backgrounds, you can insert them on the boundary conditions.
Yes.
So it's just that on top of that you will dress those background fields with fixed Chern classes,
Right.
Eiger Chern classes, with some flat fields. If you couple them to this bulk over there, no?
Yes.
So also that is allowed in this picture. You can just it's just that it is something that is related to stuff that you put on this symmetry boundary. In that symmetry boundary, this A curly A is a choice of background gauge field that you are free to choose whatever also topological non-trivial, but it's an external extra datum, which is, by the way, what a background is. So you can dress this setup in such a way that it couples to backgrounds in d dimensions by putting them on the boundaries.
Yes.
So in particular, I think that your question about the topological twist is related to choices of boundaries.
Yes.
It would be very interesting to generalize this picture to a supersymmetric model.
Right.
We'll probably have some super version of this BF theory, but then there will be also.
I mean, you're gonna work with theory in the BV formalism,
Yes.
twisted BV formalism or something like that.
Yes, and yes.
Sorry. Other questions? Thanks.
Yes.
Yes, I
Yes.
have a question about the general argument that you can relate the SymTFT picture to the holographic picture.
Mm-hmm.
So there are cases of in holography where you can have some field like a dilaton that's growing towards the boundary, and then that tells you that the coupling of the gauge fields. I don't know how obvious it is that this way of rewriting as a BF theory, and then the other term you can throw in the limit of circles, but coordinate dependent limit of going towards the boundary. That would apply in all those cases.
Very good question. In our case, one restriction that comes from holography, which I haven't mentioned, but it was on the board, is the fact that our construction, we trust it from the holographic perspective only when d is greater than or equal than 4. Because that d equal to 4 is some sort of a critical dimension for gauge theory, and where the gauge coupling is an exactly marginal parameter. Above it, it is something that wants to flow to 0. So it is in that context, if the bulk SymTFT bulk is 5-dimensional, your boundary is 4-dimensional, that's where our construction, we believe it really is effective. For dimensions lower, this is a viable alternative, but I think that there are many more options. It's like the richness of non-abelian Chern-Simons theory is somehow a hint towards that. No? So I don't know if this is related to what you are saying, but perhaps we can discuss it later.
Yeah.
Yes.
I mean, there is the interest of time. One last quick question, and then we'll close. Yes.
I want to ask, is there any SymTFT formulation for the defect to alignment? Since you mentioned defect, you also mentioned to alignment. So, in the presence of defect, there could be some new top alignment because of the defect. So people call it the defect. So you have also a new formulation in this SymTFT. Is there any SymTFT formulation?
Good question. Maybe somebody in the audience know the answer. I'm watching you. If there is a way of including defect Tuft anomalies in the SymTFT.
Tuft anomalies.
Tuft anomalies. Yes.
I think so.
Yes.
But I don't know if this has been
We never wrote it, but we know that.
Yes, exactly. so they know how to do it. It's a very natural question. So it's possible.
All right. I think everyone is eager to go to lunch.
Yes.
So, if there are further questions to that, thanks, Michele.